Okay, we are now recording. And let me share the screen. All right, so exam is next Tuesday. Game plan is 14.3 today, first half. Okay. After the break, I'm going to let you ask questions, and I'll sneak in a little bit of 14.4. I am going to give you a quiz, so I want to save time for the quiz. So if you have lots of questions concerning the Chapter 13 exam, I'm going to make a limit up to, say, 8 o'clock. I want to give you at least, say, 25 minutes to do the quiz. Okay, the quiz is not going to be on Chapter 14. It's going to be some Chapter 13 stuff. Okay. Tuesday, I'll begin lecture with 14.4, okay, for quote unquote a while, which is probably no longer than half an hour. Then I'll stop, let you ask questions. When that stops, we break and then we take the test. Okay. Again, if it looks like I'm way ahead, well, not really. Remember, I botched the schedule up from here, so I kind of have to gain a day or two. Okay, so I mean, on the original schedule, 14.4 wasn't until here, but I'm not sure if that's really true. And we have a flex day coming up on March the 2nd, it also looks like. Okay. All right, so let's knock off 14.3. Okay, maybe sneak in some of 14.4. Okay, then a question and answer session in preparation for the test. Okay, so you've already seen one exam, so you know the rules. You turn in this for homework. Let's see, 13.1 to 13.4. This is our shortest chapter. All the other chapters, again, are longer. Chapter 14 goes up to what, 8 sections? Chapter 15 has 9, and 16 also has 9. So this is a much shorter chapter. So, okay, and so since the test is next time, you may turn into homework as early as right after class. So you say, I've already done the homework. I'll take it starting once class is over, up until half an hour after the exam. Okay, so there is a 70% homework requirement. If you don't turn in at least 70% of the homework, then I don't grade your test. You automatically get a 0. And that's not hard to do considering I end up doing a huge percentage of the problems anyway, right? So 70% is not that difficult to do. Okay, so whenever I decide to start the test on Tuesday, you have until the rest of the class. That's a minimum of 50 minutes, but hopefully it could be more. So class ends at 8:25. So you take a picture on your cell phone, just like the quizzes, or if you have a scanner, you can scan. Turn in the exam by 8:30, and then another half an hour, so until 9 o'clock to turn in the homework, okay? So that's the way that works. All right, so 14.3, we're doing partial derivatives now. And really, there's only one main concept you need to know for partial derivatives. First, how do you write them? Page 914. The ones I'm going to use primarily are fx and fy, and the partial of f with respect to x and the partial of f with respect to y, the funny backwards 6. Okay. It can also be the partial of z with respect to x, partial of z with respect to y. So z is a function of x and y most of the time for us. Okay. We will have some occasion to have x as a function of y and z, or y as a function of x and z. That's just like when we were doing x and y. Most of the time we had y as a function of x, right? And then later on you said, okay, we could have x as a function of y. So likewise for us, most of the time, z is a function of x and y. Z will be the height, which is the reason why it was chosen that way. So z is the height, just like y used to be the height. Z is the height. So f of x, y, you pick a point in the plane, like the floor. Imagine the floor is the xy plane, and then every point on the plane has a point above it for a z coordinate. Okay, so most of the time I write either fx, fy, partial of f with respect to x, partial of f with respect to y, and so on. And here's the rule. Okay, do you have to write this down? I don't really think so. Once you get the hang of it, you know what's going on. Okay, to find fx, treat y as a constant, differentiate with respect to x. To find fy, regard x as a constant, differentiate f of xi with respect to y. And similarly, if you have more than one variable. Okay, so here we go. Okay, so 14.3, number 15. And oh yeah, I don't remember if I showed it to you last time, but just in case, make sure I get everybody, those of you that don't have the book and don't plan on getting it. Okay, so page 924, the first problem was 15. Let me look at our assignment list again. So the highest, that's 15, the highest is 65. So 15 through 65, the odds. Okay, then over here, and let's see, 65 was the highest. So I think you can see 65 now. Okay, so there we go. All right, f of xy is x to the fourth plus 5xy cubed. Okay, fx, partial with respect to x, that means y is a constant. Treat y as a constant. So when you see 5xy cubed, the coefficient is 5y cubed. Pretend it's 5y cubed, a constant, times x. Okay, so differentiate with respect to x. X to the fourth is 4x cubed. This is 5y cubed, a constant, times x. Therefore, the derivative is 5y cubed. Now, fy, the partial with respect to y. X is constant, that means x to the fourth is constant, so its derivative is 0. So forget about it. 5xy cubed, so the coefficient is 5x. So the derivative is 5x times the derivative of y cubed, 15xy squared. Okay, that's the way it goes. Okay, 21. F of xy is x over y. I'm going to write it as xy to the negative 1. Makes it a little bit easier that way. Okay, partial with respect to x, fx. That means y is a constant. That means y to the negative 1 is a constant. It's basically coefficient times x. So the derivative is just the coefficient, y to the negative 1 or 1 over y. Fy, the partial of f with respect to y, that means x is considered constant. So x is like the coefficient. Pretend it's 5 or something. So you go negative 1 times x, negative x, y to the negative 2, and then just clean up the algebra, negative x over y squared. Okay. Takes maybe a little while to get used to it, but if you get the hang of it, it's fine. You just have to pretend that other letter is a constant. I mean, if it helps you, just pretend it is a number. Just temporarily pretend it's 3 or negative 5 or something like that. Okay, 25. G of uv is u squared v minus v cubed to the 5th power. Okay, so you know there's going to be some chain rule involved. It starts off the same for both of them. So by the chain rule, you go 5 times the derivative of all this stuff raised to the 4th power, all this to the 4th power, and then by the chain rule times the derivative of the inside, and then for the derivative inside, that's where you have to determine whether you're differentiating with respect to u or v. Okay, so g sub u, partial with respect to u, 5, blah, blah, blah to the 4th power, right? Times the derivative of the inside with respect to u. So with respect to u, that means v is considered a constant. It's like constant u squared. So the derivative is 2uv. The derivative of negative v cubed with respect to u is 0 because that's all constant. Okay, so that's basically it. Just clean up easy stuff like 5 times 2 is 10. So final answer, I did 10uv and then u squared v minus v cubed raised to the 4th power. Okay. Now g sub v, the derivative with respect to v. Okay, so right now you can't just say the derivative of g because there's 2 parts. That's why we say partial derivative. Okay, they're full derivatives. It's not like half a derivative when we say partial. They're full derivatives, but there's 2 parts. There's a u part and a v part. There's an x part and a y part. Okay, or maybe later there's an x, y, and z, or x, y, z, t, or whatever. Okay. All right, g sub v. the derivative with respect to v, that means u is constant. So it starts off the same, right? To differentiate this, it's blah, blah, blah to the 5th power. So that part's the same, 5 u squared v minus v cubed raised to the 4th power. And then again, by the chain rule, it's times the derivative of the inside with respect to v. So if I differentiate with respect to v, u squared is a constant. So it's just like saying, what's the derivative of 6v? 6. So what's the derivative of u squared v? U squared. And the derivative of negative v cubed is just negative 3v squared, and that's it. Okay, and there's no reason to go any farther. You can just leave it like that. That's pretty much it for that one. Okay, then 33, you have a function of 3 variables. W is natural log of x plus 2y plus 3z. Chain rule again. So that means in each case, you start off with 1 over, right? 1 over that, and then times the derivative of this expression with respect to whatever you're doing, x, y, or z. All right, so what's the derivative of w with respect to x? You go 1 over x plus 2y plus 3z. That's how you differentiate ln, right? Then times the derivative of the inside with respect to x. That's 1, that's nothing, so 1. W sub y, same thing, 1 over x plus 2y plus 3z, and then times the derivative of the inside with respect to y, that's nothing, and what's the derivative of 2y with respect to y? 2. And for the same reason, w sub z is 3 over the same thing, right? Derivative with respect to z, 1 over x plus 2y plus 3z, times the derivative of the inside with respect to z, so that's nothing, and that's 3. Okay, so I have 1 over, 2 over, 3 over. Okay. All right, 37, a little bit harder. You have a function of 4 variables. Okay, just show that to you quickly. Where to go? 39. Oh no, 37. H of x, y, z, t. X squared y cosine of z over t. Okay. By the way, if you were to go to a 4th dimension, normally that would be time. Sometimes people say time is the 4th dimension. Okay, a function of x, y, z, and t, time. Okay, so example might be a temperature function. Here's a point in space, right? So you want the temperature at the x, y, and z coordinate, but you also want to know the time, right? Because depending on the time of day, maybe it's warmer. It could be the very same spot, same x, y, and z coordinates, but the time is different. So if the time is different, the temperature will be different, right? If it's in the middle of the day, it's going to be warmer, and in the middle of the night, it's going to be colder, right? So you have a function of x, y, z, and t, perhaps. So h of x, y, z, t, x squared y cosine of z over t, and the best way to treat this as z times t to the negative 1. Okay, and as is my convention, I like these better, but once in a while, I'll do the backward 6 just to let you know it exists. Okay, so partial derivative of h with respect to x, the funny backward 6, it kind of looks like a d or a partial d because we're doing partial derivatives. Okay, so the language we would say is the partial derivative of h with respect to x, or the partial of h with respect to x, the funny backward 6. Okay, with respect to x, that means all of this is constant. It's constant times x squared. So how do you differentiate x squared? 2x. So 2x, and just copy the rest of it. Y cosine of z over t. Okay, partial of h with respect to y. So look at y. Everything else is a constant, which means essentially it's constant times y. So I think to myself, 3y. What's the derivative of 3y? 3. So what's the derivative of all this other stuff, which is constant, times y? It's all the other stuff, which basically means just drop the y. x squared cosine of z over t. Is that right? Because everything else is considered constant. Okay, and the derivatives with respect to z and t are a little bit tougher because they're tied up with a cosine, but x squared and y is considered constant. Okay, differentiate with respect to z. So think of it as z t to the negative 1. So x squared y being constant, leave that alone, x squared y. Derivative of cosine is negative sine. So I've got negative x squared y sine, right? Of that function, z over t. And then by the chain rule times the derivative of the inside with respect to z. So treat it as z t to the negative 1. It's constant times z. Therefore, the derivative is a constant, t to the negative 1. Or 1 over t. Okay, so one more time. The derivative of this with respect to z. So x squared y is constant, just copy it down. Derivative of cosine is negative sine of the same thing, z over t. And then by the chain rule times the derivative of z t to the negative 1 with respect to z is t to the negative 1 or 1 over t. Okay, and a little bit of cleanup. I made this as negative x squared y over t, sine of z over t. And finally, differentiate with respect to t. So again, treat this as z t to the negative 1. Okay, so once again, it starts off with x squared y. It's a constant. Like pretend it's at 7. If it's 7 cosine, you would leave the 7 alone, right? And then differentiate cosine is negative sine of the same thing, z over t. And then times the derivative of z over t, z to the negative 1, with respect to t. That's why it's better to write it like that. So differentiate with respect to t, it'd be negative 1 times z, negative z, t to the negative 2. Is that right? So there it is, negative z, t to the negative 2. I messed up at first here. Okay, so overall, I now have a positive, got a double negative there, minus and a minus, so positive x squared y z, t to negative 2 comes downstairs. I messed up, or pretend it's a 1. So x squared y z over t squared, sine of z over t. Okay, let me raise it up again. I'll raise all this up for focusing purposes. So a lot of what I did was blurred. So you can check the video later if the focusing wasn't to your satisfaction. Okay. Okay, 39 is actually easier than you might think. (39) u equals the square root of x1 squared plus x2 squared plus dot 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 plus xn squared. Okay, you don't even know how big n is, but it doesn't really matter. Okay, you just do one of them, and once you do one of them, you get the hang of all of them, essentially. Okay, treat this as blah 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 to the 1/2, right? Square root means 1/2. So the partial of u with respect to x1, the first variable, is 1/2 blah 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 to the negative 1/2. And then by the chain rule times the derivative of the inside with respect to x1. So if it's with respect to x1, all of these are constant, forget about it. The derivative of x1 squared is 2x. The 2 cancels to half, so that leaves me x1 on top, and square root of x1 squared plus x2 squared plus dot 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 plus xn squared is on the bottom. Okay, that's the partial of u with respect to x1. You can tell the exact same logic works for every single one of them, x2 and so on. So in general, the partial of u with respect to xi, call it xi, is xi divided by the square root of x1 squared plus x2 squared plus dot 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 plus xn squared. Okay, so that's the derivative in general, it looks like. All right, 41, a little bit harder function. They have r of st. So yeah, obviously you want to get some comfort in having letters other than the ones that we're used to. Okay, so we're used to Z, X, and Y, but you can have S and T. Okay, find the indicated partial derivative. Okay, so the first problems, 15 through 39, of which I already showed you several, just find a derivative. Now 41, find a derivative at some particular point. That's just like in Calc 1, where we said, okay, f of x is equal to, I don't know, x squared minus sine x plus ln x. Find a derivative, okay? And then you said, okay, find f prime at 2, then you plug in 2, right? So that's what's happening now for 41. Find a derivative and then plug in 0 and 1, right? Find a derivative at a specified ordered pair. All right. All right, so R of st is t e to the s over t. Treat that as st to the negative 1. Again, that's probably a little bit better. St to the negative 1. So I want the derivative with respect to t. Okay, there's a t here and a t here, so I have to do the product rule, right? First function, second function. So copy the first and then times the derivative of the second. So what's the derivative of e to the s over t? E to the s over t. And then by the chain rule, it's times the derivative of the exponent, which you want to pretend as s t to the negative 1. So what's the derivative of s t to the negative 1 with respect to t? It's negative s t to the negative 2. Okay, so one more time, product rule, first function, second function. So copy the first function, t, and then times the derivative of the second. Derivative of e to the s over t, the way exponential function works is e to the s over t. Then by the chain rule times the derivative of that exponent, s over t, pretend it's that. So it's negative s t to the negative 2. Plus second function, copy the second function, e to the s over t, times the derivative of the first, but the derivative of t is just 1. So there we go. Okay, clean up the algebra here. I messed up again. What's new? Okay, so let's see. It's negative s t e to the s over t divided by t squared plus e to the s over t. Okay, and yes, I could clean this up, but you really don't have to. Very fortunately, I can just plug in now. Okay, 0, 1, that's s comma t. So if I plug in 0 right here, that wipes this whole fraction out, right? Which is nice. So that's 0. And here, put a 0 and a 1, you're left with e to the 0. So it's 0 plus e to the 0, answer is 1. Okay, so you're finding a derivative at a particular point right now. Okay, so 43 is similar. Okay, it's tougher because you have a function of 3 variables, f of x, y, z. Well, that's okay, no problem. And they're asking you for fy at 1, 2, 2. So one particular point in space, okay, here's a dot. What's the derivative in the y direction, specifically in y? Okay, so this thing's so messy. I'm glad they didn't ask for fx, fy, and fz, or using the backward 6 notation, right? The partial of f with respect to x, the partial of f with respect to y, the partial of f with respect to z. They're only asking for one of them. So here's a function at one particular point in space, 1, 2, 2, right? 1 out, 2 right, and 2 up. There it is. And you only want a derivative in the y direction for this particular graph. All right, so first thing I'm gonna do is properties of logs. Okay, it's way easier if you split this up. Remember the log of a quotient? Ln of a over b is ln of a minus ln of b. So it's the ln of the top minus ln of the bottom. That's way better than trying to take it all at once. Okay, so ln of the top minus ln of the bottom. Okay, now yes, it's gonna be messy, but after we plug in, hopefully it's not so bad. Okay, how do you differentiate ln? 1 over. So 1 over, I don't have to write the 1 because it's being multiplied by something. So 1 minus radical x squared plus y squared plus z squared times the derivative of the inside with respect 2y. Okay, we only want the derivative with respect to y. Derivative 1 is 0. Okay, remember this is blah, blah, blah to the half. So half comes down, negative a half, x squared plus y squared plus z squared to the negative a half times the derivative of the inside with respect to y. Derivative of the inside with respect to y is 2y. Never mind about that, that's constant, so its derivative is 0. Never mind about z squared, its derivative is 0. And something similar over here, minus the derivative of this thing. Okay, so first you go 1 over 1 plus radical x squared plus y squared plus z squared. Again, by the chain root times the derivative of the inside, it's almost the same, except instead of a minus, it's a plus. So derivative of 1 is 0. Derivative of that is 1/2 x squared plus y squared plus z squared to the negative half, again, times 2y. Okay, and a little bit of cleanup. That 1/2 will cancel that 1/2. That 1/2 cancels that 1/2. Okay, so I'm just going to write this as a negative y. I'm going to leave that alone. Y, leave that alone. Okay, and I think it's easier now if you just plug in 1, 2, 2. Okay, okay, 1, 2, 2. This is a mess. This is a mess. This is a mess. This is a mess. But let's get rid of it right now. 1, 2, 2. 1 squared plus 2 squared plus 2 squared. 1 plus 4 plus 4 is 9. Right? One more time. Put a 1. 1 squared is 1. 2. 2 squared is 4. Another 2 squared is 4. So 1 plus 4 plus 4 is 9. So I'm going to change that to 9. That one to 9. That one to 9. That one to 9. So that's what I did. Okay. So it's 9 to the negative 1/2. 9 to the negative 1/2. Okay. Oh, and y. Y was 2. So I changed that to 2. That's 9 to the negative 1/2. That's 2. 9 to the negative 1/2. 1 minus square root of all that stuff. Square root of 9 is 3. 1 minus 3. 1 plus 3. Okay. Let's see. What am I doing here? This is negative 1. Negative 2 divided by negative 2. That thing that I have circled. Negative 2 divided by negative 2 is 1. So it's 9 to the negative 1/2, which means 1 over square root of 9. Minus, that's also 9 to the negative 1/2, square root of 9 on the bottom. That's 2 over 4. 2 over 4 is a half. So that's 1 over 3 minus 1 over 6, which finally is 1 over 6. Okay. So yeah, that was kind of a mess, but we got it. Okay. Okay, that's the idea behind partial derivatives. That's what's happening here. Okay. Now, a little bit more. 53. Second partial derivatives. You're going to have a first derivative. You're going to have second derivatives. It's not really that big a deal. Let's see, where can I find it in text? Page 918, higher derivatives. fxx, fxy, fyx, fyy. Okay. So if you have a function of 2 variables, you can have 4 second derivatives. See, second partial derivatives. fxx, take the derivative with respect to x, then take the derivative again with respect to x. fxy, take the derivative with respect to x, follow that up with the derivative with respect to y. fyx, take the derivative with respect to y, then take the derivative with respect to x. fyy, take the derivative with respect to y and differentiate again with respect to y. So you have 4 second partials. Okay. If you have a function of 3 variables, I'm not going to write them down. Function of 3 variables, f of x, y, z. How many second partials do you think there's going to be? It's going to be 9. basically you have 3 choices for the first derivative and 3 choices for the second derivative, right? So we can have x, xx, xy, xz. Then you can have y, x, y, 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 z, and then z, x, z, y, z, z. Okay. Okay. I'm not going to use this notation or this notation. I am going to use this. That kind of looks like the d squared y over dy squared, the Leibniz notation in Calc 1, right? This is the Leibniz, the d stuff, Leibniz notation. Right, remember for the second derivative, you put the 2 on the top here, but the bottom 2 goes over here. Remember that weird way of putting it? Second derivative, second partial of f with respect to x, second partial of f with respect to y. Okay, now this might get a little bit complicated. This is really what it means. Okay, you take the partial with respect to f with respect to x, and then the partial with respect to y. So when you write it with the funny backwards d, you actually go from right to left. Okay, this one and this one is obvious, right? Whether I write it like that or like that, the first and fourth ones, you know it's going to be x, x, and the last one is y, y. Unfortunately, this notation is left to right, x, y, y, x. When you write it with the d notation, the Leibniz notation, it actually goes from right to left. So this means you take the derivative with respect to x first, and then you take the derivative with respect to y. Okay, so that's how you write the second derivatives. Which one do I prefer? Of course, the fxx, fxy, fyx, fyy. It's easier, as you might guess. Okay. Turns out this is not as big a deal as you might think, and we'll see why. Okay, so let's try some second derivatives. All right, so let's see, what time is it? Okay, we're good. So I'm pretty much done with the 15 to 43 type. So 53 to 65. Okay, 53, find all the second partial derivatives. Okay, now, if I got a question like that on the test, and that's not on this Tuesday's test, it's the test after that. Can you guess how many total derivatives do I have to take? Hint, you can't get the second derivatives without the first derivatives. Okay, the directions right here imply 6 total derivatives. So if I were to ask you a question exactly like this, find all the second partial derivatives, you need 6 derivatives. You need the derivative with respect to x, fx, and the derivative with respect to y, fy. And once you have that, you have 4 more derivatives, right? fxx, fxy, fyx, and fyy. So 6 total derivatives. Okay, and that's part of the reason why I say, okay, you know, the third exam and on, maybe those exams are longer because it's just more stuff to do, in which case I may give you the entire class period for those exams. Okay. Okay, so first I need fx and fy. So partial with respect to x, that means y is constant. For x cubed y, minus 2x cubed y squared is constant, 6x squared y squared. Okay. Fy, take the derivative with respect to y, that means x is constant. It's basically constant times y, so the derivative is just a constant, x to the fourth. That's like saying, what's the derivative of 5y? 5. Okay, if it helps, just think of a number. You know, take a number example. Okay, derivative with respect to y, that means all of this is constant. So you're differentiating y squared. So it's 2 times all that. So minus 4x cubed y. Okay, now for the second derivatives. fxx. I take the derivative with respect to x. Here it is. And I differentiate again with respect to x. So look at this. 12x squared y. Derivative with respect to x minus 12xy squared. Okay, fyy. Start with the derivative with respect to y. Here it is. Differentiate again with respect to y. So that's constant. That means it's 0. Derivative of that is 0. The derivative of this is just negative 4x cubed y because it's constant times y. So the derivative is just a constant. Okay. Now fxy. Take the derivative with respect to x. Here it is. And now differentiate with respect to y. So derivative with respect to y is 4x cubed. Derivative with respect to y, negative 12x squared y. Finally, fyx. That means I take the derivative with respect to y. Here it is. Differentiate with respect to x. Okay, derivative with respect to x, 4x cubed. Derivative with respect to x, negative 12x squared y. And there we go. Okay. And what do we notice about those 4 partial derivatives? Well, that's different. That's different. The mixed partials, these are sometimes called the mixed partials because you're mixing x and y. They are equal. Okay. Is that always the case? It's always the case for us. You can actually contrive of a weird function where this is not true, but it's really weird indeed. If you have most quote unquote normal functions, this will always be true. Okay, so that deal that I just mentioned before about going backwards, right? That you're supposed to go right to left instead of left to right. It's not that big a deal because it actually doesn't matter. Okay, fxy is going to be fyx. Okay, in general. Okay, on page 919, that's something called Cleros Theorem. You can put it down, but I don't think you have to. It's pretty easy to memorize. The mixed partials are equal. Suppose f is defined on a disk D that contains the point A, B. If functions fxy and fyx are both continuous, then fxy equals fyx. Okay, all the functions are going to that we will deal with behave that way. Okay, so Cleros theorem, fxy equals fyx. So you may use that as an assumption now. Of course, you may want to just do it. Just do fxy and fyx to show that they hopefully are the same. Okay. All right, so that's that. Let's see. Why are second partials the same? Okay, so we won't have occasion to prove it, unfortunately, and I don't think the book does either. It's, let's just say it's beyond the scope of our course to show that. Okay. Oh, and yeah, I should hasten to add, they're not always true. Like I said, you can make up a function, but it's going to be a weird function. Okay. Put it this way, if you ask me right now to come up with such a function where it's not true, I can't make one up on the spot. Okay, I can't give you an example. It is that unusual for it not to be so. Okay. All right. Okay, what time is it? Oh, soon. Didn't quite finish before the break, but that's okay. Okay, 57. Okay, maybe I'll do this and then we'll break. V equals sine of s squared minus t squared. So a little bit tougher. So V sub s, derivative of sine is cosine. So cosine s squared minus t squared times the derivative of the inside with respect to s, 2s. V sub t starts off the same. Derivative of sine is cosine. Cosine s squared minus t squared times the derivative of the inside with respect to t, negative 2t. Okay. Then the second partials are going to be harder, of course. It looks like they may involve the product root, right? Okay, so VSS. Take the derivative with respect to s and differentiate again with respect to s. Product root. So first function, 2s, times the derivative of the second. So derivative of cosine, blah, 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 is negative sine, blah, 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 times the derivative of the inside with respect to s, 2s. Plus second function was cosine s squared minus t squared times the derivative of the first function with respect to s. Derivative of 2s is 2. So that's just going to be 2. Okay, a little bit of touch up. That's going to be negative 2s times 2s, negative 4s squared sine of s squared minus t squared plus 2 cosine of s squared minus t squared. V sub tt, sorry, I messed up here. You can see what I have here. So V sub tt, take this and differentiate with respect to t. So that should be a negative t and another negative, sorry, negative 2t, another negative 2t. All this junk here should be negative 2t, negative 2t. So one of the negative 2t's is the first function. And then the other comes from the chain rule times the derivative of the second. So the derivative of the second is negative sine s squared minus t squared times the derivative of this, which is a negative 2t. Okay, and actually, I think I messed up again. Yeah, sorry, I had it right at first. There's going to be 3 negatives total. Let's see if I got that right. Okay, there's a negative for there, another negative for the derivative of cosine, and another derivative for negative t's. Right. Okay, so I think I had it right at first. There's 3 negatives. So it's a negative of negative 2t times negative 2t. Okay, then second times the derivative of the first. Right, so second function was cosine of s squared minus t squared times the derivative of the first, which is negative 2. Okay, so put it all together. If I did it the right way, I've got a triple negative. So negative 4t squared sine of s squared minus t squared minus 2 cosine of s squared minus t squared. And then the mixed partials aren't really that bad, I believe. Okay, VST. Take the derivative of this with respect to t. That's nice. That does not involve a product group because then you can just treat 2s as a coefficient. Okay, so differentiate with respect to t, 2s, negative sine of this thing, and then times the derivative of the inside, which is negative 2t. Okay, so that comes out to be 4ts sine of s squared minus t squared. I did that. So one more time. Differentiate with respect to t, 2s is constant. So leave the 2s alone. Derivative of cosine is negative sine, so negative 2s, sine of blah, 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 times derivative of the inside with respect to t, that's negative 2t. So that makes it positive 4ts sine of s squared minus t squared. Okay. All right, I think this is a good place to break. Okay, and I'm actually almost done. So we'll break. I will do a little bit more after the break, and then I'll let you ask questions up until 8 o'clock, and then I'll give you a quiz on the previous chapter. Okay. All right, so let me shut this down. Break. It's, well, right at 7. A little bit more. Okay, how about 7, 7:12, 7:13, maybe something like that. Okay, I'll put that in the chat also. Let's say 7:13. Okay. Okay, folks, I'm going to start up again. So I only had a couple more problems to do. So that shouldn't take that long. So I will knock off 14.3, give an introduction to 14.4, tell you what the formulas are that you need. And then after that, I'll let you ask questions, which can be 0 questions or all the way up until, let's say, 8 o'clock at the latest. So I have enough time to give you the quiz. Okay. Okay, problem 61. All it asks is verify the conclusion of Cleros Theorem that is u sub xy equals u sub yx. That means I don't have to find all 6 derivatives. I don't need uxx. I don't need uyy. I need u sub x, I need u sub y, and then uxy and uyx. That's quote unquote all. Okay, so 59 and 61. 61 looks harder, so I'll do 61. Okay, so u is cosine of x squared y. So partial with respect to x. Derivative of cosine is negative sine, so negative sine of x squared y times the derivative of the inside. Let's see. I think I got this wrong. Let's see, u sub x, derivative with respect to x. So negative sine, negative 2xy. Okay. I think I botched this up. Should be negative 2xy. Okay, so I'm gonna have to do this on the fly, unfortunately, I guess. U equals cosine x squared y. So I may have totally botched this up. So u sub x, derivative of cosine is negative sine x squared y times the derivative of x squared y with respect to x. That's 2xy, right? So what I have here is incorrect, it looks like. Negative 2xy sine of x squared y. U sub y starts off the same, negative sine x squared y times the derivative of the inside with respect to y, that's going to be x squared. So negative x squared sine x squared y. So hopefully I did that right. So sorry, I have no confidence in this at all now. So u sub x y. So I start off with the derivative with respect to x. Here it is. And now I differentiate with respect to y. So that's going to involve a product. Okay, so first function times the derivative of the second. Derivative sine x squared y is cosine x squared y times the derivative of the inside with respect to y. That looks like it's going to be x squared. So that gives me a grand total of negative 2x cubed y. Cosine of x squared y. All right, u sub yx. U sub yx. Start off with this. Differentiate with respect to x. Okay, product rule. First function, negative x squared, times the derivative of the second. So derivative of sine is cosine x squared y times the derivative of the inside with respect to x, 2xy. All right. Plus the second. So this is the second function, right? Sine x squared y times the derivative of the first. So the derivative of negative x squared is negative 2x. Okay, so let's see. Something's not right here. uxy. I didn't do the second times the derivative of the first for uxy. Sorry. Okay, first times the derivative of the second. Yeah. I'm messing this up totally. Plus second times the derivative of the first. So second sine x squared y times the derivative of the first with respect to y, negative 2x. Okay, so if I don't mess up anymore, negative 2x cubed negative 2x cubed y cosine of x squared y minus 2x sine x squared y. See, negative 2x cubed y cosine x squared y minus 2x sine x squared y. Okay, let's look at negative 2x sine x squared y, negative 2x cubed y cosine x squared y. Okay, so they do match. So I think I finally got it. Which again goes to show you, show all your steps. If you got the basic idea and you messed up somewhere, I mess up all the time. So I would try to be as generous as I should be with myself, since you have already found out very early that I'm nowhere near perfect in doing all this stuff. Okay, so show all your work. You'll get partial credit if you got the basic idea. Okay. Okay, then finally 63, and that's the last one I was going to do. 63. Find fxx and fxyx, third derivatives. Right? So 63, x, then x, then x, and then x, and then y, and then x. Okay, shouldn't be that bad because it's a polynomial. And yeah, I messed up again here. X to the fourth y squared minus x cubed y. Okay, first find fx. Take the derivative with respect to x. So 4x cubed y squared minus 3x squared y. Okay, fxx. Differentiate again with respect to x. 4 times 3, 12x squared y squared minus 2 times 3, 6xy. And then fxxx, differentiate this again with respect to x. So 2 times 12, 24x y squared minus 6y. Okay, that's done. Then fxyx. So here's fx, fxy. So I differentiate this thing with respect to y. So 2 times 4 is 8, 8x cubed y. Derivative with respect to y, just drop the y, negative 3x squared. Right? It's constant times y, derivative is a constant. And finally, fxyx, I differentiate this thing again with respect to x. So 8 times 3, 24, x squared y minus 6x. And that's pretty much about it. Okay, so I'll show you that. Okay, so this one I totally botched right here. So I think I was okay up for the first derivative. So go from here to here and raise that up for focusing purposes. And then even there, I supposedly fixed it, but even within the fix, I messed up. And there's that. Okay, so hopefully that is enough of that. Okay, so I am now officially done with section 3, folks. So that's as much as I was going to cover. All right, so I'll do an introduction to 14.4 and then let you ask questions. So it won't take me that much longer. So if you have questions pertaining to the test, you can start putting in the chat even now if you wish, up until a limit of 8 o'clock. And so if it stops before 8 o'clock, then we'll just go straight to the quiz and then we'll call it a day. Okay. All right, so what's 14.4 about? Okay, page 927, tangent planes and linear approximations. Okay, now in Calc 1, we had tangent lines. Okay. Now we're going to have tangent planes. And yes, we've already done linear approximations before. Okay, so if you imagine something in 3 space. Okay, now in 2D, so by analogy, y equals f of x, you had a tangent line, correct? Tangent line. Well, in 3D, okay, now I can't draw, I can only draw quote unquote simple stuff. So let me just draw a sphere. Okay, take a point in the sphere. There's now going to be a tangent plane. If you can imagine, just resting, you're just resting something on the ball, so to speak. Okay, you have a tangent plane. So tangent plane. Just like over here, you have a tangent line. Here you have a tangent plane. Okay, and the book does a pretty good job of the picture here of tangent planes, page 928. Okay, the tangent plane contains tangent lines. They call it T1 and T2. That picture doesn't do so good, but this should do a better job on page 929, where they're zooming in. Okay, so you have the function here and see the tangent plane, and then they're zooming in and they're zooming in more. And as you zoom in more and more, look at letter C, right? Compare A. So A goes from what? I don't know, -4 to 4 for X, -4 to 4 to Y, and -20 to 40 for Z. Then B, they zoom in more. And then C, they zoom in more. And by the time you get to C, they look like they're almost touching, right? You may have tried this by analogy on a graphing calculator, right? If you zoom in real close on this region, it almost looks like a straight line, right? That's the tangent line. So that's the same concept over here. We're zooming in to get a tangent plane. Okay, what is the tangent plane? Okay, so they go over a little derivation of it, right? We've seen this before. In fact, you might have this on the next test, right? A, x minus x0 plus b, y minus y0 plus c, z minus z0. Okay, they do a little bit of algebra and some argumentation here, but here's the result that you're going to put on the next formula sheet. Again, I don't blame you if you don't even look at this until after the test, but this is what we're going to have for the tangent plane. Z minus z0 equals fx, derivative with respect to x, at x0, y0, x minus x0 plus fy at x0, y0, y minus y0. Okay, in fact, in my opinion, it's easier to not even have these. Just write z minus z0 equals fx, x minus x0 plus fy, y minus y0. In other words, this equation, just leave off the parentheses x0, y0. Okay. And again, proceed by analogy. If you only look at this is exactly what you had in Calc 1, was it not? In fact, that almost looks like y minus y1 equals derivative x minus x1. In the x direction, that would be true. If you're only going in the y direction, that's like y minus y1 equals m times x minus x1, or in this case, z minus z0 equals the slope in the y direction, y minus y0. Okay, so in general, you just put them together. Okay, very analogous. Okay, remember the point slope form in algebra 1, right? Y minus y1 equals m times x minus x1. So this is the tangent plane. Z minus z0, fx, x minus x0, plus fy, y minus y0. Okay, I mean, there is good reason to put the x0, y0. It's to remind you to plug in. But that's almost like when we were doing y minus y1 equals m times x minus x1, right? You never leave the answer with an m. You plug in what the value of m was, right? You say, I figured out the m was 4, then you would put in 4, right? Okay, then you also have linear approximations, and you did this in Calc 1, page 929. Writing it as a function, L of xy, the linearization is 4x plus 2y minus 3. That's the same tangent plane written as a function, which basically means isolate the z. So for over here, see the z minus z0? Just add the z0 to both sides and clean up the algebra. And you have z equals f of xy, or more accurately, L of xy. That's just like the linearization you had in Calc 1. Okay. So see, we have f of xy is approximately 4x plus 2y minus 3, which means if I'm very close to the point in question, rather than using the function, which might be more complicated, I will use the plane, 4x plus 2y minus 3, because I like that better. And you see, that's called the linear approximation or tangent plane approximation of f at 1, 1. And that's exactly the same thing as you did in Calc 1, right? And some of Calc 2. We say, okay, instead of using the function itself, because it might be messy, it's got trig and logs and exponentials and fractions and square roots. Okay, let me replace it with the tangent line. Y equals mx plus b. We like y equals mx plus b. Okay, so in a small neighborhood, very small region, right? You can use the straight line approximation. Then, of course, if you stray away too far, then the approximation is no good after a while. Okay, which is exactly what's happening over here. Okay, for picture C, the plane and the function itself seem very close. Okay, but if you get further and further away, like A, and say after a while, okay, they're not close at all. Okay, so you may be asked to write it as a linear approximation. And that's basically what's going on. Differential, page 932. Okay, remember in Calc 1, you did differentials. dy is f prime of x dx. Here was a picture that you had in Calc 1, where delta x is the same as dx. What's the difference between dy and delta y? Delta y is the actual change in the curve. Dy is what happens if I pretended it was a straight line and I stayed along the straight line. Okay, so we had dy equals f prime of x dx. Okay, an easy way to remember that is pretend it says dy dx, the Leibniz notation. Right, we already know dy dx is f prime of x. If you multiply both sides by dx, so to speak, then it looks like that. Okay, so if you just go to one more dimension, here's the analogy. dz is, and in this case, it's probably easier to look at this, partial of z with respect to x dx plus the partial of z with respect to y dy. Okay, and it kind of looks like what you did in Calc 1. That looks exactly the same as that, except the backward 6. And it kind of looks like that the dx's cancel out, right? And here the dy's cancel out. So you have the net change in z. Okay, so on your next formula sheet, dz equals either this, but I like this better in this case, because it kind of looks like they cancel out. Partial of z with respect to x dx plus partial of z with respect to y dy. And as you might imagine, if you have another variable, then you just put that other one after that. Okay. Function of 3 or more variables. Completely analogous. Page 934. Give you a function of x, y, and z. So they call it dw. So why do they pick w? Well, I guess if you go in alphabetical order, you're supposed to pick the next letter, but there is no next letter after z, right? You go x, y, z. Okay, you say what comes after Z? Well, we ran out, so they switch over to W. That's all. So this is just one more variable. So dW is partial of W with respect to X dx plus partial of W with respect to Y dy plus partial of W with respect to Z dz. Okay. In fact, if you're going to put something on your cheat sheet, this might be the better one. This is a 3 variable case. If you go to 2 variables, you just knock off that one and you essentially have that. Okay, the only thing is that other variable might be Z instead of W. But you can see the progression. This is one variable. In fact, you can even write this as dy equals dy dx dx. I'll write it in my book. It looks like you cancel out the dx. F prime of x is the same as dy dx, right? So dy is dy dx dx. It kind of looks like, oh yeah, you just cancel the dx's. So now you have 2 variables, partial of z with respect to x dx, partial of z with respect to y dy. And if you have 3 variables, there it is. dw is partial of w with respect to x dx plus partial of w with respect to y dy plus partial of w with respect to z dz. Okay, and that was my introduction to 14.4. And Tuesday, I'll get started on some of these homework problems. Okay, all right, so I'm done. I'll let you ask questions now if you wish. So again, the game plan for Tuesday, day of the test, I'll lecture on 14.4. I'll do some of the homework problems. I've already done your intro. Then let you ask questions, we break, and then we take the test. Okay, so I'm letting you ask questions Tuesday also, but I'll take any that you might have now up until a limit of 8 o'clock. I'll give you the quiz. Okay, so you can start putting stuff in the chat if you wish. And let me see what we got here. Okay, 13.3, number 47. And yeah, the only questions I want today are from chapter 13, nothing on 14, please. Okay, 13.347 was asked for. Let's see what that's about. Oh yeah, that one. Let's see. I don't want to recreate it, so I'll just grab my notes on that if I can dig them out. So that might take a while. Sorry. I'm afraid if I started from scratch, I might mess up again. So 13.347. Let me try to look back at my notes on how that went. Okay, now since I did it before, I'm going to go faster. Plus, it should be on a previous video. Okay, so this, you're at 1 2/3 1, so t is 1. Okay, so first I find r prime. So differentiate all these guys, 2t squared 1. Okay, unit tangent vector is take it and divide it by its magnitude, which is 2t quantity squared, 4t to the 4th. Or 2t squared is 4t to the 4th. This thing squared is 4t squared. 1 squared is 1. This factors into 2t squared plus 1 squared. So I'm dividing all of these by 2t squared plus 1. Okay, and then t of 1, just plug in 1. That's going to be 2 over 3, 2 over 3, 1 over 3. Then you have to find all of these derivatives. Yeah, that's going to be a while. I'll just tell you, this one involves a quotient root. That's probably the hardest. Okay, it came out to be that. Okay, these were easier. This one, the trick was to add 1 and subtract 1. And this one, pretend it's 2t squared plus 1 to the negative 1. Okay, so anyway, quotient root, plug in 1, came out to be negative 2/9. This one, I rewrite this as this. Okay, and you plug in 1, you get 4/9. And then this one, differentiate, Plug in 1, you get negative 4/9. Okay, so you have negative 2/9, 4/9, negative 4/9. Okay, to find a unit normal vector, you divide by its magnitude. 4/81, 16/81, 16/81. That comes out to be 36/81, which is 6/9. Dividing by 6/9 is the same as multiplying by 9/6, which basically means cross off all the 9s, make them 6s in the bottom. So I have negative 2, 6, 4, 6, and negative 4, 6. Okay, and then B by definition is T cross N. So T cross N. So that minus that is negative 4/9 minus 2/9 is negative 6/9. Then J is negative that, negative 4/9 minus a minus plus 1/9. And then 4/9 minus a minus 2/9, 6/9. So negative 2/3, 1/3, 2/3. Okay, so that's as much as I'm willing to do for that, especially since we did it previously. Okay. Okay, 13.2, number 5, 13.3, 19. Okay, let me see. (13.2), number 5. I'm gonna have to close the chat again. Sketch the plane, find r prime of t. Okay, so e to the 2t I plus e to the tj, t equals 0. (13.2), number 5. R of t is e to the 2t I plus e to the tj at t equals 0. Okay. Okay, sketch the curve. So let's see. I can write this as e to the t squared e to the t. And e to the t is y. So x equals y squared. Okay, so we know it looks like that. Okay, except both x and y are positive because e to anything is positive, so this part's not really there. Okay, t equals 0, I'm at the point 1, 1. All right, so that's what we have. And so sketch the graph, I did that. Find r prime. The derivative is 2e to the 2t, e to the t. And r prime of 0, plug in 0, and you get 2, 1. So 2, 1, that's 2i plus j, so crudely speaking, that's like that. So there's r prime. And sketch the position vector and a tangent vector for the given value of t. Okay, so position vector always starts with the origin. So there's r prime. And yes, that does look like, you know, it's going along the tangent to the curve right there. Okay, so I think I did everything you asked for. Yeah. Raise that up a little bit for you. Okay, 13.319. 13.319. Okay, radical 2t, e to the t, e to the negative t. Okay. Find the unit tangent and unit normal vectors and find the curvature. That does look familiar. I think I already did this one before also. Let me check back my notes. 13.3. Did I do this one? Looks like I did not do it. It's very familiar. Oh well. Just go with it. Okay, so R prime is radical 2 e to the t negative e to the negative t. Unit tangent vector means divided by its magnitude. Square root of this thing squared plus this thing squared plus this thing squared. And this very conveniently is e to the t plus e to the negative t quantity squared, which means t of t is radical 2 over e to the t plus e to the negative t, e to the t over e to the t plus e to the negative t, e to the negative t over e to the t plus e to the negative t. That's t of t. And let's see, the unit normal. Well, because of time, I think I'm going to have to not do that, because to differentiate these is going to be quite a bit. See, you're not just doing one, you're doing three. This one's not so bad because that's a constant. Okay, these are much worse, so to speak. Okay, so I'm afraid because of time, I'm going to have to say I'm not going to do that. But we have the formula n of t is t prime divided by magnitude of t prime. Okay, but to find t prime means you're doing three derivatives, two of which involve a quotient rule. This one doesn't. Okay, so I'm afraid in the interest of time, I'll just have to say etc. Okay, it's very messy work. Okay, and I don't think I'm willing to do that right now. Okay. And suffice to say, yeah, I realize that for an exam, I probably wouldn't have you do something with this many derivatives that come out bad. Okay, but for homework, it might be worth doing. Okay, for that one. Okay, so that's all I'm willing to do for that one, I guess. Okay, let's see, 13.319, that was that. Okay, and yeah, all right, got that. Okay, so I think I'm caught up there. Did I catch up? It's hard for me to check the chat at the same time. I think I'm caught up. Okay, anybody else want to ask me something? What time is it? Okay, so 10 minutes more, otherwise we'll go straight to the quiz. You can still ask next time. Okay, so again, next time I'll do 14.4, question and answers, break, and then take the test. All right, and then as soon as class is over, I'll start taking the homework also if you wish. Okay, so that's it. Let's go to the quiz. So get your cell phones ready as I show you this. And this is hopefully not that long. Okay, and now I have to find where I put it. Okay, so bear with me as I go find it. Okay, here we go. Try to raise it up. Number one, give the domain of the function. R of t is natural log of t, 1 over radical 4 minus t, t over t squared plus 1. Just give the domain. You don't have to do any derivatives or something. Okay, so you have to find t which is allowed for all three of them, right? So it's no good for a t to work for, let's say, the z, but it doesn't work for x. So the t has to work for all three of them. Second one, find the length of the curve R of t is -3t for cosine t for sine t on the interval from 0 to 4. Okay, a hint is that it actually comes out nice. I can't seem to show the whole thing without getting out of focus a little bit here. Okay, hopefully you can still see that. Okay, I'll hold it for another 15-20 seconds. So try to get a screenshot or take a picture by that time. So number one, R of t, natural log of t, 1 over radical 4 minus t, t over t squared plus 1. And two, find the length of the curve. R of t is -3t for cosine t for sine t, t between 0 and 4. Okay, I will now assume that everybody has it. So get started. Let me set up your breakout rooms. And as usual, if you finish early, you can just leave and submit it. Okay. First thing you want to do, of course, is put down everybody in your team's first and last name, please. Okay, I'm stopping the share. I'm going to stop the recording.